like to learn more about Taylor's Astronomical Society, please check out our Instagram or visit our Facebook page. So today we are truly honored to be able to invite a very special guest from Starfinder Astronomical Society, Mr. Fong Keng Yin. Normally in the society, we all just call him Mr. Funky. So Mr. Funky is the incumbent president of Starfinder Astronomical Society, a society which has dedicated themselves to public outreach, spreading awareness and appreciation of astronomy to the public. So Mr. Funky, along with Starfinder, has been the organizer for the Malaysian Olympiad on Astronomy and Astrophysics, MOA, since 2017, and has since led stellar students who are awardees of MOA to the International Olympiad on Astronomy and Astrophysics, or IOAA, thrice. 2015 in Indonesia, 2017 in Phuket, Thailand, and 2019 in Caspe, Hungary. He has also led many expeditions to experience some once-in-a-lifetime astronomical events, such as the 2016 total solar eclipse in Indonesia and the 2019 annular solar eclipse visible in Malaysia. So without further ado, please welcome the president of Starfinder Astronomical Society, Funky.
Thank you, Chijong. Actually, I know Chijong for quite a while. I think since 2017, the first time you joined the IOAA in Thailand, Phuket. So he has been a very outstanding student for IOAA. He won the honorable mentions last year. So I think, one of the a very unique student. So he is a very alert person as far as the impressions to me. For other students walking on the street in a foreign country, they will just follow the leaders. They will never observe their surrounding. But he's the one who actually see where's the train is going, where's the bus is going, where's the next train to catch, and things like that. Even though he's not leading the team. So yes, I would say that he is a born leader. Okay. So without further ado, let's start the talk. Okay. Chijong, I think you need to enable the screen sharing for me in the Zoom. Screen sharing, you have to enable it. Yep. Okay.
Okay, I've enabled it.
Yes. So I think I believe you can see my screen, right? Yeah. Okay. Today we are going to talk about a few things. Okay. Basically, we are going to talk about astronomy, but most importantly is how practical use of computations and why and how in terms of applying information technology to understand the universe. So there will be some example. It's all right that you may not able to understand all of them. That's natural. A talks like this will expect whoever listen to a talk will only understand about 15 to 20%. You may have to watch it again, or you do your own research later on based on the information you receive from this talk. So I would like to introduce my society first. So Starfinder is a non-profit organization, non-governmental, founded in 2004. We have a few hundred members, active members, and we organize regular star parties and outreach activities to promote astronomy. So as Chijong has mentioned, we are the organizer of MOAA since 2017. And yeah, the objective of the society is to promote the learning of astronomy. So this is some boring information about me. So just skip it, and then we go into the top, okay? So when we talk about information, what's the difference between data and information? So I suppose everyone has a smartphone, okay? You probably subscribe to some data plan, and you can transmit and receive digital data from the internet. And this data is actually coming to you in a binary unit of 0 and 1. So yeah, the speed of transmissions depends on the current technology. The fastest we have available is 5G, but I think most commonly people are using 4G for their smartphone. So the 4G, you can transmit about 12 megabits per second. So mega millions to 12 million bits per second, and sorry, you receive and you transmit up to 5 megabits per second. So the 5G technology is actually promised to do up to gigabit. So a typical character, you need 8 bits to transfer. So 8 bits means that to the power of 8, you have 256 combinations. Okay, but 8 bit 256 combinations, you can only transmit and receive the standard characters. So now the world is actually international. Everything is international. So we have multi-culture, multi-languages, and we need characters of other languages. So they introduced what they call the Unicode, up to 16-bit or 65,536 combinations of types of characters and symbols. So at the moment, I think that's enough. So what happened is that all this data and bit come to you, they are meaningless things. They are just 0 and 1. But your phone system actually will translate them and organize them, sort them out, and present to you in messaging, in social media, banking informations, or watch Liverpool to become the champion without even playing, okay? And the apps and all these things, and present information in a very organized way to you. So when you look at the information, you either ignore them, okay, or make a decision with them. So, so such as the data bit coming to you right now, while I'm talking to you through video and through voice, you may be able to learn something about it. So discovery and knowledge is actually a way that we look at the informations and we discover things. We learn something. This is how our civilizations actually begin. So it's hard to imagine that talking about cavemen with data and informations, but yeah, let's see how it goes from here. So let's visit somewhere. I have been doing some traveling a few years ago. I've been to this place south of England, near the town of Amesbury. So this place is called, I think you all heard about it, it's called the Stonehenge, okay? Stonehenge is actually a circular complex built around 4,000 to 5,000 years ago. And the stone itself, they built this complex weight up to 25 tons, and some even up to 50 tons. And most of them is about 4 meter high, 2 meter wide. They are actually transported to the site from somewhere in Wales, about 385 kilometers away. So those are the time that they don't have any machinery, basically using manpower to build such a gigantic monument. So what's the purpose of this monument, right? So everybody is curious. So archaeologists actually discover something here. So this is a plans of the Stonehenge, okay? And when there are two significant stone, what is called the slaughter stone, okay? And there's a gap between these two stones, and 1 and 2. So at every winter, when the sun rises, the sunlight will actually come through the gap. Okay, so there is definitely a purpose and related to astronomy. As we know, sun is the nearest star to us. All right, so so the winter solstice is where the sun will start going southward in the northern hemisphere. So it is a sign that the winter will be soon over. Okay, so we'll talk about that part a bit later. So this is how it looks like. This is actually a picture captured from another picture. Okay, so what is this all about? Winter and summer and the seasons. So our Earth is actually tilted. Okay, 23.4 degree if I remember correctly. Okay, so if you look at the Earth rotates from west to east, and we have three imaginary lines that we can see. So so the upper line is where the sunlight. Okay, I'll explain in the next slide. Okay, what happened is that when the Earth orbits the sun, due to the tilt, different part of the Earth will receive a different amount of sunlight. Okay, so for example, this is during March 21st, which is during the spring equinox. The sun will be directly above the equator. So Malaysia is over here. We are 3 degrees above the equator. So we receive a direct sunlight over here. And if you look at northern and southern hemisphere through the line, this part of it and this part of it, you notice that the ray of the sun, although they started out at the same wave, it's usually spread out when it hit the surface of the Earth. So although they receive sunlight, they actually receive less sunlight than us. Okay, so in summer solstice, that the sunlight will be shining directly on the northern hemisphere. Okay, then this part of the Earth will receive more sunlight. Okay, so that is the summer of the northern hemisphere. But you look at the southern part. Look at the southern part. Let me see whether. Okay, this is, sorry, I forgot to change the slide. Yeah, let me on the cursor. Okay, so this part, can you see the cursor?
Yes.
Okay, sorry, just now I forgot to on the cursor. So over here, the sunlight is actually spread out evenly, as wide as the beam. But over here, the beam is actually cover a larger area, and over here it cover even a larger area. So over here you receive a less amount of sunlight than here. So this is the winter of the southern hemisphere. So this is the reasons why we have seasons. Okay, so this thing will repeat itself to the southern hemisphere, and so on and so forth. So so from winter solstice to vernal equinox, the sun is actually moving north and continue to move south until summer solstice. Okay, so this is actually sorry, this is animations. So if you can see the sun during the daylight, the sun actually passes through few constellations, at least 12 constellations during the path in the sky. We call it the zodiac constellation. I think everybody is familiar with that, and some of you may be checking out your newspaper what is my fortune that day based on that. So yeah, that is where people use for astrology. Okay, so if you believe that, believe until the mid of this talk, then you can stop believing it. Okay, so yeah, so summer, all the seasons actually somehow related to the sun, and also it related to these constellations. So by looking at the constellation, we actually know the season. So how? Okay, if you during winter solstice, okay, you cannot look at Capricorns, right? But you can look at Cancer. If you see Cancer in the sky, the constellation of Cancer in the sky, you know it's winter. But we can't look at Capricorns because it is daytime. But the sun is in the constellations of Capricorn. So if you are Capricornus and all those things, you were born in the month of December. This is how the zodiac works. So by looking at different constellations, you actually know the season. Okay, so let's look at another place. This place is actually in Ireland. Okay, the Republic of Ireland, and near the Bourne Rivers. So the place is called New Grange. New Grange is actually a buried ground. This thing was built about 5,200 years ago. They were built about 3,200 BC. And also during the Neolithic period. Neolithic period is still considered the Stone Age, right? So what unique about this place is that there's an opening here. So every winter solstice, exactly on that day, the sunlight will go into this opening. Okay, and any other day, the sun will not align to this opening. Again, the season noticeably is very important to those people at that time. They build structures, elaborate structures, just to know the season. So why is that so? So okay, this place I haven't been before, and this is in the southern France, and now it can't be, we can't go in anymore. It is a cave. Okay, this cave is known as La Crosse. So it was discovered by a group of teenagers during the end of Second World War. They were chasing after their dog, and they went into this particular cave. And when they shine their torch into the cave, they discovered this cave is full of cave painting. And this cave painting was dated, radioactive dated up to about 15,000 to 17,000 years old. So first thing, we know that human existed during that time, 15 to 17,000 years ago, number one. Number two, they stay in the cave, okay? Number three, they know how to paint. So we know these three information just by looking at the cave, okay? So, and you can look at the painting. They are fine arts. They are really good painting, okay? They are with colors and things like that. That means they even know how to use color to extract color from plants and things like that. So they have certain developments of intelligence and culture, right? So what they don't understand is this. Why among all these paintings, they are stick figures like this, right? Such a nice painting of a bison. Bison is like a buffalo or kind of things. Okay, there's a stick paintings, and nobody understand. So the speculation is that they must be naughty children. The parents or the adults paint something there. They also scribble something there. But about 15 years ago, one of the archaeologists who happened to be an amateur astronomer discovered something quite unique. So he examined all the cave painting and looked at the stick figure. They discovered that the fixed stick figure actually coincide with the positions of certain constellations or stars in the sky. Say, for example, in this painting here, the stick figure with the bird and the eyes here, there's a small stick figure here. You connect these three, this coincides with the summer triangle. And this is not only applicable for one painting, this is applicable for many of the paintings. So, well, we see summer triangle during summer. But like the words is the name implies, summer triangle we see in the summer. So what does it mean? So well, if we apply some logic, it could mean that we will see bison, which is next to the bison here, during summer. So after examining more and more painting, they discover that this is in a form of calendar. So 15,000 to 17,000 years ago is considered the prehistoric period of our history. Prehistoric means before writings has been invented. So it is a part of the things that started the civilizations. So we start without learning how to write, invent writing. They have a mean to record events and record events based on a date. The date is when they can see some constellation in the sky. So yeah, so if we go back to what we learned, we can see different seasons, we can see different constellation in the sky. Okay, so why is this important? Now, yeah, so okay, this is something a bit weird. Okay, let me explain to you. So during those days, those people stay in the cave. We call it cavemen. Okay, so cavemen, they live in a way that how they get food. They do a few things. So the men usually are hunters, so they hunt, and women, they stay very close to the cave. So they gather fruits, vegetable around them. So they are gatherers. So that kind of way of life is called hunter and gatherer. So somehow rather, even today's, that things has actually inherited to us. I'm not sure genetically or somehow we actually still hunters and gatherers in nature. So so just look at how we keep our tools. Say for example, your smartphone. Okay, so where guys keep their phone? So guys, tell me where you keep your phone usually.
Beside the bed.
I mean, when you go out.
In our pocket.
Yeah, in your pocket. So girls, where do you keep your phone? Hey, don't be shy. Speed up. Anyone? Okay, maybe a better question. Where your moms keep your phone? Keep her phone. Usually ladies.
They call me to hold.
Sorry? They ask you to hold. They ask you to hold. Okay. So ladies like to keep things in their handbags, right? And guys always keep things in their pocket or they hang around their belt. So this is a trait of the hunter and gatherer. Why? When men go for hunting, they need to reach their weapons quickly. Okay, their life depends on it. Okay, so the easiest way is to keep somewhere that you can reach as quick as possible. So it's always put in your pocket, or if no pocket, hang on your belt and things like that. Okay. For ladies, they are gatherer. So they gather fruits and they need something to keep the fruit. They usually have a basket. So they pluck the fruit from the tree, pluck the mushroom, pluck the vegetable, they throw into the basket. So today's, that's the handbag. Okay, I don't make it. I didn't make this up. Okay, somebody actually came out with this hunter-gatherer thing. So I just relate to you. So hunter-gatherer ways of life is also is not a very stable way of life. The reason is that when winter approach, all the animals will start migrating away from the place that is cold. So they move south. In the northern hemisphere, they start moving south. And when they move south, you will have no food. And also the plants also die. You won't have fruit. You don't have vegetable. You have to move south as well to follow the animals. So when more and more things moving south, the place become crowded and become dangerous. So you probably have a tribe of 100 members moving south during winter when the weather get cold. When you come back, you may be left about 60 of them, okay, and things like that. So it is a very dangerous thing to do. So the main reason you have to move is because the food resource become less. So you have to move. And the weather become cold and you need something to protect yourself. The main reason is always food, okay? So the discovery of seasons have helped civilization to take a foothold rather than start migrating. They learn how to plant with seasons. So you can actually sow the soil, sow the seed, plow the soil, sow the seed during when spring ended, okay, during summer, and you harvest it during autumn, and you can store food during winter. So you don't have to move anymore. The first thing, the breakthrough is that they look at the constellations, they know when and when season, what season it is now, and when the next season going to start. They can actually predict that. So from a hunter-gatherer a kind of way of life, it can become a farming way of life. So the life become more stable and people stop dying, the population start to increase. So those people that understand astronomy will become more prominent in their society. And because of the stable, you don't have to move around, people have more time to get more knowledge. So starting from a farming community, eventually it become a town become a country. So this is the start of civilizations, thanks to astronomy, okay? So yeah, this is the progress of human until what we are today. Okay, so the key thing is that we started out with somebody curious enough to look at the sky and look at all these constellations. These are the data they receive, okay? And some of them bother to organize them into a cave painting. So they turn the data into informations. And somehow they discover that everything happened around them is actually a cycle, okay? So a cycle means that the things will repeat, that the whole process will repeat 365 days later. So a year later, the whole thing will repeat. Oh, they understand this is a cycle. Then, well, civilization somehow get a foothold and we become an intelligent species rather at distance ourselves, distinguish ourselves from the animals around us. Okay, so all right, so this is the one that we actually look at it, but something extra here. Okay, so this is the zodiac that supposed to look like at now, rather than a few thousand years ago when we discovered the zodiac constellation. So there are some extra constellations in the chart here, in this diagram here. Okay, so hold on, is my cursor still on? Yeah. Okay, so you can see here something extra here and something extra here. This is Ophiuchus, I think it's pronounced Ophiuchus, and this is Orion. And what happened is that the Earth, anything that's spinning, will actually wobble around its axis in a process called precessions. So this wobble process is actually complete. We complete one cycle in 26,000 years. Okay, because of precessions, we move a degree every 72 years, and the zodiacs were invented 3,000 years ago. So the vernal equinox was supposed to be in Aries, but now it's in Pisces. So now our northern star is called Polaris. In 10,000 years later, the Vega on Lyra will become the northern star. Okay, so there's a problem. So we now know that astrology has a problem, right? So how astrology began is something like this. There are two types of people, as far as I know. The clever one will realize that the constellation change against season is just a cycle. However, there are those who believe that, well, the constellations are message from the heaven who tell us how to do things. So if they can tell us when to plant, they must be able to tell us, predict other things in life for us. So this group of people created astrology, okay? And now more people are believing in science, but there are still many believe in astrology. So this is actually the constellations that the present zodiac constellations now. One of them is actually Scorpius. Scorpius is actually, the sun will be in Scorpius for only 6 days, but it will be in Ophiuchus for 19 days. So we should technically have either 12 or 13 zodiac now. So either we remove Scorpius or include Ophiuchus. Okay, so if you can't find that in your daily astrology predictions, so you know something is wrong. So in astronomy, we believe in real science, not make-believe kind of pseudoscience. All right. So this sum up what I just said. Okay. All right. So let's look at some science now. Okay. So let's say you ask a question: how do we know sun has hydrogen? So we heard of sun is powered by the fusions of hydrogens turned into helium and things like that. And we also say that sun is very hot. How hot? How do we know? So usually, how do you test hydrogen, right? So in order to test hydrogen, you have to you burn hydrogen and you hear a pop. You light up something with hydrogen gas, you hear a pop. Then you know you have there's hydrogen there. And how do we measure temperature? You use a thermometer, right? But we have a problem here. If you want to answer the questions the question just now, okay, we have to collect a sample from the sun. Okay, so I don't know how feasible it is, but somehow, okay, we don't have a way that safely collect a sample from the sun. Okay, well, maybe Malaysia can. Okay, so how do we actually do this to prove that? How do we observe, or how do we get a sample to test that theory the sun is actually has hydrogen. And how do we measure the temperature? So here comes this guy. So this guy is Isaac Newton, okay? And this guy, he's a lucky guy. He stay in UK, stay in England, where there's no durian tree. So he was hit by an apple, and he survived, and he discovered gravity. Okay, so so he also discovered something. So one day he put a prism and let the sunlight come out, and he see a spectrum of colors projected, okay, on his chair, right? So sometimes I ask, how many colors uh, the sunlight has? A lot of people say 7 colors. It's actually not true, okay? It's a progressions of colors from light red until bright red until purples, blue purples, and things like that, right? So the reason people tell you in 7 colors is that when they look at the spectrum itself, you see dark lines. These are divisions of different colors. So give you the impressions there are 7 colors. Okay. So well, let me explain physics theory. I'm so sorry I have to tell you this, but yeah. Okay, so what happens is that in the sun is is powered by something that very hot, okay, and it's so hot that the energy is able to remove electron from the gas, okay. So when the light that shine through this gas with the electron with the electron removed, how it removed is that this gas absorb a photon with the same energy required to remove the electron. So when the sunlight pass through this gas, it leave a gap. Okay, so this is how you created the black color. Okay, so this is what we call absorption line. So the gas in front of the light absorb the energy. So the light that transmit to you is actually without that portions of the energy. So it become a black line, a dark line. So in the spectrum, you see as a dark line. At the same time, the gas eventually will get back his electron. So when he get back electron, he will emit a photon with the same energy or mimic a color, the missing color here. Okay, so we will use that later on. Okay, so this is a simple explanations of this process, emission and absorptions. All right. So so from on Earth, we actually can simulate this. So I think some of you, if you are doing your science students, you have done this before. You put a gas discharge tube and lit it up, and then use a prism. You can see that you project all this color light. This is emission. So this is this part, the emission. So if you have a bright light behind it, then you'll see the gap here. It becomes a black line. So it itself is an emission. So you can see different elements will project different emission line or absorption line. So we have, this is the periodic table with all the emission spectra of different elements. So basically this is the fingerprint. So if you observe the line in this way, you know this is hydrogen, okay? So what we do is that we pick a prism and look at the sunlight, and we actually can break down hydrogen. There's an absorption line here, okay, and things like that. All right. So where are the absorption line? You've got hydrogen everywhere. Okay. So we prove that well, we have hydrogen in the sun. So how about to prove the temperature? Okay. So we look at flame. Okay, fire. Fire, sometimes you see fire at different colors. It's actually the different color actually represent the different temperatures. So this is called the Wien's law. Okay. Yeah. Again, sorry. I do not want to. I mean, overwhelm you with too many formulas, but probably some of them, your science student, you have learned about this. So every temperature will peak in different colors. Okay, so if 5,500 degrees is green color, 5,000 degrees is actually yellow color, and so on and so forth. So we actually can observe the sun colors to determine the temperature. So that is somewhere here. Okay, the sun color is somewhere here. The sun actually greener than what we thought. Okay, but due to a mixture of reflection and all these things, we can't actually see it. But if you can measure it, it's about here. Okay, 5,000 over degrees. Okay, so actually 5,800 degrees Kelvin. But the Wien law itself is also approximations. Okay, so in essence, what we are learning now here is that in astronomy, we can't usually collect sample and prove something. We have to depend on observation. Doing that, we have to understand and accept certain scientific laws. So scientific laws, there are a few very important things we need to agree on to do that. So first of all is in scientific law, we say that scientific laws are law of physics or law of science. Many laws of science is actually universal, meaning that the science on Earth is a science same as a science anywhere in the universe under the same condition. Okay, that's first universal law. So the second one is that simple. What is simple? Simple is that if there are 10 explanations of a phenomena, the simplest explanations shall be the truth. Okay, shall be the best explanations of the phenomena. So say example. Okay, well, I can't really think of example. Never mind. Let's go on. The third one is absolute and stable. So absolute and stable means that the same, if you have the same parameters, okay, you should get the same results. Okay, so no matter how many times you test it the same method, you get back the same result. So whatever you've been testing is actually absolute. Okay, it shall not change if you test it with the same way. Okay, and the fourth one is actually general conservative of quantity. So this is actually like in momentum or in energy, the quantity may be changed, but the total quantity of a system doesn't change. So for example, like okay, you drive a car, you put your fuel inside the car. So the fuel itself is actually store chemical energy. So that chemical energy, when you start your car, you burn the engine, it creates kinetic energy, it created a heat energy, but the total from the chemical energy conversions to the heat and the kinetic energies, the total is the same. So basically, the energy is actually conserved. All right. Okay. The last one is actually reversible in time, as that time itself is irreversible. Well, this one is okay. I'm talking to you at 4:52 now. All right. So if we take a video tape now and you reverse back to 4:52, there was a time that I'm talking to you, right? We can, but the time itself cannot be reversed. The event has happened. So if you go back at that time, the event happened at that time will not change. Okay. Of course, there's a weird thing about in quantum mechanics. This has exceptions. In quantum mechanics, there can be the time itself can be changed. Okay, so I mean, like the Ant-Man's event in Avenger Endgame says, it sounds cool to add the word quantum in every sentence. So I just try to sound cool today. Okay, in physics, there's something called observable. Observable is a physical quantity that can be measured. So in our example early on, the observable is actually the light itself. So we actually can measure light in many ways. So first thing we can measure light is measure the kind of colors of the light, and we can actually measure uh, uh, the energy of the light. Okay, so that reduces the temperature itself of the sun. So what is actually light? Okay, so light is something that a bit difficult to explain. So light is a form of electromagnetic wave. So electromagnetic wave is something that the electric field oscillate perpendicular to a magnetic field, so create electromagnetic wave. Okay, so and it has a progressions that perpendicular to these two elements. Usually you can describe with Fermi. I think it's right hand rule, right? If I'm not mistaken. So light itself can also describe by particle theory. So this is the image of a photon. Okay, so we also can say that light that you see is actually consists of photon. All right, photons is particles of light. So this is a combinations of what actually experiment that actually they try to photograph light. They discover that photon is actually progress in a way that manifest itself as wave. Okay, so don't worry about that. We just need to understand a few things here. So basically what we see is that from radio wave to gamma ray, is actually they are all electromagnetic wave, or they are photon with different energy. Depend you want to follow the wave or the energy, photon concept. Okay, both are acceptable in science. But in fact, they are just a way to explain it. The actual things can be accepted in quantum mechanics. Okay, so our visible light is here. Okay, between 400 nanometer and 700 nanometer. So this is a wavelength of the electromagnetic wave. So we can, as we look at it, this is the wavelength and this is the frequency. So when you see a wave, is you have the wave is something that you go up, come down, and go up again. This is one cycle. The length of one cycle is 400 nanometer, and it go about hertz is how fast it go, how many times it go in 1 second. So it's defined in hertz, and you see that wavelength, shorter wavelength, okay, shorter wavelength, okay, a very high frequency, and they are the most energetic. Okay, they carry out energy. Okay, and radio wave basically are very long wavelength, and they have a very low frequency. Okay, so they are less energetic, right? So visible light is around here, and your mobile phone or the one that you use to cook your food, the microwave is around here, the microwave wavelength. So energy, the high energy is actually gamma ray and also X-ray. These are considered a higher energy emissions. All right. So on Earth, we are protected by the atmosphere. The atmosphere actually blocks many of the electromagnetic wave, except for some radio wave and the visible light. So one of the reasons we see this, our eyes is actually evolved to see this because of our atmosphere and also the emissions from our sun. So if you grow up in other planets, which is dominant probably the infrared, so our vision will be adapt to that through evolution. So we stay in Earth, so we see this part of the spectrum. If you grow up in another world, in another system, dominated by different emissions, your sensor will be actually, in theory, evolve around that. Okay, so this is the part that we do most of our astronomy observation. Okay, now, so how do we acquire data? So today we talk about data. So the data we acquire is photon. So we are talking about optical, okay, optical observations. So obviously we use something called the telescope, okay. So this is a telescope in Lake Observatory. You see the guy standing there on the. So this is how big this telescope is. So there are many things that are observable here. So we can actually measure the magnitude. That means how strong, for example, a star, how bright is a star. You can measure the color of the star or any celestial object, and you can analyze the spectrum, the absorption line, what absorption line you have, and you can actually measure the separation between two objects, the size of the object through astrometry, and of course, beside the emission, which is the broadband emissions emitted by heat, you have very specific emissions. So we look at what is all these things means, right? So usually emissions by heat is called a thermal radiation. So basically, it's a very broadband emission. So it is also most of the light we observe, we see from the sun come from this emission or come from the star based on these emissions. But beside that, behind that, actually the sun and a lot of celestial objects also emit in other form. So they also emit in radio wave, but our eyes can't see radio wave. Our equipment can detect it. So they also emit infrared and also other radiations. So the thermal radiation is actually a very broad band, cover different wavelength altogether. So there are also non-thermal radiations caused by other physics process. So I'm not going to that because that we will end at 8 o'clock tonight. So just remember that we have thermal and non-thermal kind of emissions from celestial objects, right? So this is a Crab Nebula. This is a picture I took using my telescope. And this is the one that taken by various telescopes, including most of them are space telescope. So if you look at the optical window, so which is only okay, go back here. So over here, our atmosphere actually absorbs all these things. So in order to observe, we have to send a spacecraft above the atmosphere. So these are space telescope, different of space telescope. Of course, the most famous one is actually known as the Hubble Space Telescope. Okay. So in the old days, when you do observation, I mean, you actually keep a record of your observation. So this is also in Lake Observatory. So this is a logbook they use for observation. So this is how they keep the data itself, what they see, and they also take a photograph of it. So those days, before digital data, this is actually a photography plate that using chemical reaction to capture the image. Okay, so this is how data were recorded 50 years ago. Okay, so but modern day we do it slightly differently. So nowadays what we use is called, we use digital data. So what is digital image? So surprisingly, digital image, the way that we convert image to digital was invented before digital sensor was created. So it's quite unique way is that in 1957, there's an engineer called Russell Kirch. he made a drum with a single photo detector. So the drum itself will scan a picture part by part, detecting various brightness reflect off the picture and record it in numbers. So 93 means that this is actually 8-bit data. So you have 256 level of brightness. So this is a brightness level 93. So a darker part will be brightness level 10. So using that method, you can actually form a picture, and this picture can be stored digitally. So what's the advantage of doing that? Okay. Okay, so look at this first. So digital data, the level of different level of brightness depends on how many bits of data we are storing. Okay, before that we look at character. We say that 8-bit character we have 256 level different combinations. Same as 8-bit data, we have 256 level of brightness. For a 16-bit data, we have 65,536 level of brightness. Okay, so the more bit means that we can distinguish different level of brightness better. So this is, but in digital, everything is actually based on based on bit 0 and 1. It's just that how many bits that you use, okay, to actually refine the data. Okay, now so in many years later, I think 12 years later, okay, so I think we should go back in time. So sorry, Albert Einstein is very famous about his theory of relativity, his mass and energy equations. But there's a discovery that his first discovery is less known to many. So his first discovery is called photoelectric effect. So what he discovered is that quite similar to what I explained for gas, the absorptions. So this is on a solid. So in some material, some elements, when the photons strike an element, if the energy is right, it can displace an electron. Okay, so this is called photoelectric effect. So the different elements will have a different energy level, depends on the combinations of compound element itself. So in 1971, so 1969, sorry, 1969, there are two guys, also engineers, Willard Boyd and George Smith. They discovered that silicon have the properties to displace the electron in silicon can be displaced by visible light. So they created a sensor called CCD. The full name is charge coupled device. So this is a CCD. Basically, it makes of silicon dioxide, and they have a way to store the electron displaced by the photon hitting the silicons. So by measuring how much electron, they know how much photons had hit the silicon itself, the sensor itself. Silicon is also the same. Actually, you look at a solar cell, they are basically similar to a CCD or a CMOS. Okay, they work on the principle of displaced electrons. So when the sunlight hit the silicon, they create electron, and we can use it and turn this moving electron into to power our house and things like that. So it's the same thing for CCD, the camera sensor, and for the solar cell. These two are actually based on the same principle. So the silicon sensor, base sensor, actually can measure the electron, can measure the number of photons received on this spectrum. That's the visible light. Okay, so what happens is that when we do observation, we have a process. We collect all this data from the sensor, and we go through a complicated process to derive the data and turn them into information, right? So these are some of the process that we do. Okay, so what is the advantage of digital data is that, what's digital mean? They are basically numbers. So what numbers can do is that we can do arithmetic, mathematics on it, and we can process those data, analyze them. So let's look at what we usually do. So when we take pictures of any celestial object, we collect photons. Basically, we collect photons emit from the object. Okay, so for example, I want to image a particular nebula called Network Nebula. Okay, the nebula is very small. It's only here. So this is the summer triangle. If you know how big the summer triangle, you can visualize how small is this particular section of the sky. Okay, so you started that you have a sensor here, a camera through a telescope. You can collect the data. Okay, this is my telescope, and this is a monochrome sensor, which is only collect black and white. So here is a filter view that we can selectively collect data from different spectrums. So let's say I want to collect the emissions from hydrogen gas. I can use a H-alpha sensor. So this is what I'm going to do. So here I collect, I take an image, okay, over here. This is from the H-alpha emissions of the nebula itself. So all these photons coming there, we actually go through my telescope, enlarge my telescope, and hit my sensor, and my sensor will collect all the data and form this image. Okay, so besides collecting the data, we also collect some other information to calibrate the data. So don't worry about it. We'll look into it in a short while. So when we collect data, we not only take one single picture. The reason is that we take a lot of pictures on the same thing. So we take a lot. The reason is that we want to increase the signal to noise ratio. So as we collect more data, the signal increase and the noise decrease. So what is noise? Well, there are different type of noise. So say for example, when I taking picture, suddenly there is a little bit of cloud. So they block a part of my picture, right? So when I take a second picture, the cloud will have moved to a different position. And we take the third picture, the cloud could be gone. So if I take a lot of pictures, okay, and I average out the data, because there are numbers, I can add all of them and average them out. When I average out this thing, the number, I get more signal data than noise data. The cloud will disappear. Okay. All right. So the process that we actually get rid of all the noise and carry the data itself, we call a data reductions in digital image processing. So basically, we will take the scientific data minus whatever noise of the sensor and whatever imperfections of the optics like dust, and we perform mathematics basically on this data. So we can do subtractions, multiplications, and voila, you get a picture like this. Okay, so the thing is that with digital information, a lot of things can be programmed and processed by computer, and you can even do it automatically because of that. All right. So we talk about collecting informations from visible light through accumulating photons. So can we actually collect wave, electromagnetic wave? So we say that lights have two properties, wave and particles. Let me have some water first. So electromagnetic wave can be collected using an antenna and some electronic. So basically, the method we actually collected is called the resonant method. So when electromagnetic wave pass through something like antenna, it creates a resonance, and the resonance can be recorded in the waveform. So in photon, we actually in particles way of collecting data, we actually collect amount of photon. In this case, we collect how strong is the magnetic wave based on time. So this is a time domain kind of data collections. Okay. So in astronomy, besides the optical telescope, we also use a radio telescope. They are basically a big antenna pointing in some celestial object, and the signal is amplified and recorded. So each antenna itself, a big dish like this is equivalent to 1 pixel. Okay, it's unlike your photon collection. We have a matrix. We can collect a whole picture at one time. For radio antenna, radio astronomy, we collect 1 pixel at a time. So this antenna, after collect, you will start to move to point to different part of the object, and you start collecting again. So the data is actually acquired based on a time domain way. So the whole progress of the wave is actually based on time. So the accuracy the accuracy of collecting data is depends on how good you point the antenna and how fast is your computer system collecting the data. Okay, so this is a Park telescope that we use to it collect wavelength between this 150 mm to 400 mm. It has a resolution of about 786 to 1572 arcsecond. Alternative, they have two types of I mean, this is in arcsecond, this is in arc minute. So the diameter of the antenna is 64 meters wide. Okay, so this is the data they usually we collect. So you look at it, this is time. So the strength of the signal at certain time, okay, is collected. So once the data is collected, they have to be correlated and turned into an image through a mathematical process. Okay, so one of the favorite thing that radio astronomers like to do is observe things like the neutron star that's spinning around. So neutron star is a star that is actually collapsed and in a supernova, and since after collapse, it spin around. So when it spin around, it projects a beam of radio wave emissions happen to be towards Earth, and we can actually receive the signal. So so this is animation is explanations of the neutron star. So the reason they have emit a beam of radiation is because of very strong magnetic fields and also due to their rotations. Okay, so a moving magnetic field that create the beam itself. So when the beam switch through Earth, we can actually hear them. So this is how I don't know whether you can hear it. Please let me know. I want to play it. See, this is the original data that we received. Can you guys hear it?
Could you replay?
Play again. All right.
Yeah. Nope.
Can you hear it?
Nope.
No, I think you can't hear. I don't know how to. Maybe because I share screen, it cannot be heard. Is there a way to set it? So basically, there are two files here. This file is original data. This is the processed data. So the data has been processed and also stepped down to an audible sound. So we actually give him a name called the pulsar rock. Unfortunately, you can't. Okay, I will.
Well, how about you play it and see if we can hear it?
Okay. I can hear it. I don't know whether you can hear it. Anything?
Could the participants like hear it?
Any guys can hear it?
Oh, nope. Sadly, it can't. It.
Okay.
Yeah.
Maybe I will just post the file somewhere that you can pick it up later on. All right. Okay, never mind. We can move on. So this is a picture of the Milky Way. I built myself a radio telescope that I built myself using very cheap components. The antenna is actually a used astro dish, and it took about I think about 8 months to 9 months to collect the data. And during that time, this is the Milky Way, okay, and this is the sun that passed through the Milky Way, and the radio telescope doesn't move. So we based on the rotation of Earth to collect all this data, and these are the missing parts of it. The missing part of it is because my system hang, and these are some missing part of it. Okay, so yeah. All right. So when I study radio astronomy, that time in that semester, or in Australia we call it the teaching period. During the teaching period, I have these questions. So we use photoelectric effect to collect data, collect photon, okay, and you use wave resonance to collect wave, electromagnetic wave. So can we use photoelectric effect to collect radio wave and wave resonance to collect visible light in terms of collect data from visible light? So let's look at this. So this is a radio wave, okay? So it's from 1 mm to 10 meter long. So they are very low energy, and there is no elements will emit of electrons when hit by all these things. Okay, if this thing element exists, so we'll just put it anywhere. You touch it, you feel a shock. Okay, because it's emit electron when they hit by a radio wave, and this radio wave is surrounding us everywhere. So such material doesn't exist. So how about building something antenna that can receive optical light, visible light? So the consensus of the professor and all my classmates is that no, it can't be done because it's too small. Okay, and the interference itself the cell interference will eliminate all the data. You can't do it. Well, they speak too soon. Okay, by the end of the semester, the teaching period, somebody who is also a former student of the same university that went to, who is now who was that time doing his PhD at MIT, actually came out with this thing. So it's called resonant optical antenna, and this antenna is going to use in a project called LIGO. stands for Laser Interferometer Gravitational Wave Observatory. And at that time, I have totally no idea what is gravitational wave. Okay, and few years ago, it was the biggest discovery in astronomy. So yeah, never say no. Okay, so well, since we are talking about gravitational wave, let's look at how we sometimes need to manage how we look at data. Okay, so I will use an example of explaining general relativity to do it. So see how the two things relate. So it's okay. Suppose that suppose that you can see me standing in this classroom in front of a whiteboard. All right. So in front of the whiteboard here, I'm talking to this empty class. Okay. So I move around and I move around. I move to 3 different places during. So in T0 I was here, T1 I was here, and T2 I was here. So in different time I was in 3 different positions in space and different position in time. So each of them we call it an event. So when you have a space and time, you can define space and time of something that happened, we call it an event. So event number 1, I'm here. Event number 2, I'm here. And event number 3, I'm here. So to describe the 3-dimensional space, usually we use a coordinate system that X, Y, and Z. Okay, X, Y, and Z to describe a 3-dimensional world. So yeah, so well, basically in the scenario here, if you look back, I am not going up and down. I am actually never go up and down. I only go 2-dimensionally. So the data in Z itself is not important to me. So basically, I can eliminate Z. Okay, so I can squash it. So when I squash it, I'm moving this way. I don't sacrifice any detail on this diagram, despite that I get rid of one set of data, which is Z data. Okay, the reason I do that is because I need to able to present another data, but in our world, it's very difficult to present the other data. The other data is actually time. Okay, so by eliminating the z-axis, I can replace it with a time axis. So at this time I was here, at this time I was here, and this time I was here. Okay, so if you have sometimes you may, when you do analysis or you want to understand something, you have to look at the data itself. Some data could be less useful to you and be replaced by more important data. Okay, so let's see what this leads to us. So this is an explanation on general relativity. So let's say there is a very high mass object, say planet Earth. Okay, let's say this is planet Earth in 2 dimensions. So it's a sphere in 2 dimensions become a circle. Okay, and this is the time axis. And we have a person not very quite far away from this object. So you look at the fabric of space itself and fabric of time and space itself is actually flat. But when this guy approach very close to the mass, the high mass object, the fabric of space-time get distorted, and let's say he has a time is this short. His time here will be dilated. So we call this time dilation. All right. So basically, the clock here is actually different from the clock here. The time here will be moving slower, and the time here compared to the time here. Okay, so yeah, if you have a twin and you send one out of space and the other one live in Earth, Earth have gravity. So when 2 years later, when the fellow come back from space, sadly he's younger than you. Okay, so this is how time dilation works. So this is one way of understand general relativity. But what I'm trying to demonstrate here is that how you actually can get rid of some data to get important data to understand the concept. Okay, so just now we were talking about LIGO. So this is LIGO, and this is actually it is actually a very big observatory. So the LIGO itself is actually a 3-kilometer line here. So these two things extend 3-kilometer line, and they project laser beam, and the laser beam will interfere itself and detect by this sensor. These two sensors will detect the interference pattern created by these two lasers. So yeah, this is what they have detected. Okay, this is what they have detected on 14th of September 2015, and they detected this event just for 7 milliseconds. So based on the data they detected, okay, they did a simulation. It's actually, they found out that it's a mergers of two black holes. Okay, and besides they have detected it at the same location in the sky, another telescope also detected a strong gamma ray burst. So they gamma ray burst. So they know that it is actually some event happened there. So this is the first time gravitational wave is detected in a few years ago. So this is a great discovery in astronomy. All right. So yeah, so the data is that they collect all these vibrations in the space-time, and what they discover is the mergers of a black hole. Okay, yeah. So the mass. One thing about that is that one thing about and data analysts nowadays is we can do a lot of simulations. So if you do not know an information, you can do a reverse simulations. Reverse simulations are using the known data and trying to find a fit to the observed data, and you know that you are right, or you can get extra data out of it. So for example, based on the data they receive from here, okay, they do not know the mass of the black hole. So what they do is that they do simulation with different mass, and finally they found that, okay, these are the simulated data predicted, and this is the observation data. If these two match, meaning that the mass that created the simulation is the mass that the actual event happened. So this is called reverse simulation. All right. So these are the discovery of the black hole. All right. Okay. Yeah, I want to move a bit faster now. This is the last part of it. Okay. If you look at the astronomy community, people are spending a lot of money building larger and larger telescope. So this is the size of a tennis court. This is the size of a basketball court. So these are the size of different telescope around the world. Okay. So I think my telescope will be just a pixel in this diagram, and this and their name is quite funny, right? European Extreme Large Telescope. Okay, and yeah, so the biggest one, this biggest one is called Overwhelmingly Large Telescope. So if they build another one larger than this big telescope, I don't know what they're going to name it. So why they are building, this is a China Fast Telescope, and this is Arecibo telescope. These are radio telescope. So this is actually built in a valley. in Puerto Rico. Okay, so it's not a very steerable telescope. It's like it depends on the rotation of Earth to point it itself. Okay, so yeah, just now I actually wanted to explain this thing. So electromagnetic wave can be combined. So when they are and they can destroy each other, depend where how they line up. So they can line up in different phase. So in this case here, if two electromagnetic phase in the same phase, they will combine into a bigger, stronger signal. And if they are opposing in different phase, they can eliminate itself. So if they combine, we call it a constructive interference. If they eliminate themselves, we call it destructive. Okay. So yeah, I mean this. So when you have a interference, you can actually emerge as what they call a diffraction patterns. So this is a diffraction pattern created by a single aperture, so one telescope. Okay, so never mind about this. Okay, so why we're talking about diffractions is that if you need to resolve two objects that are very close to each other, okay, say for example these two stars, they are very close to each other, they are 0.7 arc second. So what is arc second? If you extend your arm, fully, you stick out your little finger is considered 1 arc degree. So 1 arc degree has 60 arc minutes. 60 arc minutes divided again, you have 60 arc second. So using a 200 mm telescope, you actually can see these two stars independently. But a smaller telescope, you can't. You will see them as one. You cannot actually resolve it. So this is the capability to separate two very close objects. We call it the resolution of the telescope. Okay. So there's another way that's why everybody is building larger and larger telescope, because they want to resolve very small detail very far away. So there are actually another way to do it. So you look at this. If we have two opening with the same distance as the first one, you also create a diffraction pattern. Okay, quite similar to the first one, meaning that you can put two telescope with the distance similar to a single telescope apart, two small telescope, you can create the same resolution. Okay, so this type of method is called interferometry radio telescope. Okay. And this is what exactly what they did for a project called the Event Horizon Project. Okay, so let's go to that. I'm so sorry. This is the Event Horizon Project. So in the Event Horizon Project, they got the first image of the black hole. Okay, so yeah, I know there's a lot of memes about this. Okay, people put the black holes like flying eggs or all those donuts and things like that, and it doesn't look very impressive. But the way they do it is actually it is. Okay, so how they do it is that in order to create a resolution to observe this black hole, they have to put telescope very far apart. So the Event Horizon Telescope is spanned around the globe. So you can see telescope create a very long baseline. So they put one telescope here and one telescope here. So is equivalent to a telescope as large as the diameters of the Earth, right? So that is how interferometry works. So by doing that, they have to collect all the data, and they have to shift all this data to a center to correlate from different radio telescope, and they form the image that we see, the donut that we see. Okay, so it is the amount of data is up to a petabyte. So I'll come into that soon. Okay, so yeah, so first, before they even do that, they actually do a simulations. So you guys are, if you are physics students, you always draw ray diagram to see how the ray is reflected or refracted through lenses and all those things. But if you are gamer, you also know about ray tracing. Ray tracing is practically simulate or predict how the lights through reflection. So for example, in this case, if you know a light somewhere here, you actually can simulate how the shadow will look like, the actual shadow will look like. Okay, it's actually should be like this rather than this. Sorry, this rather than this, and like this car, there's an explosion, the reflections through the light, how it will look like. This is called ray tracing. So they did a simulation. Okay. So through doing ray tracing. So we know the physics about black hole, how light can be bent by the black hole. So doing ray tracing, they actually can simulate how the event horizon telescope will image the black hole and how the image will look like. So this is how they do the ray tracing. So this is before they even get the first image, they predicted this is how it looks like. Okay, that is actually from the YouTube. You can look it up yourself. Okay, so there's a person. I think what's her name? Katie something. I forgot her name. So she's the one who wrote the programs to extract the data. She didn't do. I think it's Katie Boga, something like Bosha, Katie Bosha. She wrote the program to actually extract the data from different radio telescopes and combine them. But she's not the one who do this simulation. There's somebody else. Okay, so the last part of this talk is talking about technology. Okay, so we have a problem right now. The data that we're collecting, they are growing. Okay, so these are different astronomy projects and their data they have collected. Okay, so this is a project in the 90s. They only collect 3 terabyte of data. So your normal hard disk, 1 terabyte is about 3 hard disks. So the 2MASS, okay, this is also another sky survey. They actually image the whole sky. They collected 10 terabyte of data and so on. And the event horizon collected 5 petabyte of data. So what is petabyte? Okay, this is petabyte. Okay, 1,000, this is 1,000, million, billion, trillion. I don't know how to say anymore in English. Okay, so they collected that kind of data. So the upcoming project like the square kilometer array, which is a telescope about the size of a square kilometer in size, is going to collect that much data. So we have a 4 very major problem here. The volume of data. So how big is the volume of data we are expecting? Okay, which is you can see here. Okay, so the motivations of collecting so many data is that we can do in using small data. We are only testing one hypothesis, and you big data we can run multiple testing in multiple hypotheses in an automated form. We don't have to do testing one by one. We can do it everything. And small data is that your data have to be very good. In big data, like just now I show you, we can actually average the error, average the noise. So you actually improve quality with very big data. Okay, so the motivation is to collect more. And in small data, you working a very limited data, so you have to deduce many of the results. And this one you don't have to, because there are so many things. If if certain results are overwhelm the other ones, you know this should be the answer of your experiment. Okay, so this is actually the data library of the Event Horizon telescope. So each telescope, there are 8 telescopes there. Each telescope have 32 hard disks. Okay, sorry, each telescope has 128 hard disks, and all these hard disks are helium filled. The reason they are helium filled because they have to use in very high altitude, and some radio telescope like Atacama is actually few thousand meters above the sea level. Okay, so for 8 telescopes, there are actually 1,024 hard disks to collect all the data. Okay, so massive data. Okay, the other problem they have is the variety of data. So this is a 2 mass. As I told you, it's a sky survey. Yeah. So you look at the data definitions dictionary. So there are a total of field, not much. Okay, just for the one field. So the variety of data, I mean, during my time, it considered a lot. Okay, so let's look at this. This is another data access that you can access to different telescope in the world. Okay, so let's see. All right. So you can choose any telescope, any data set that you want. Okay, let's see what we have. Gemini, maybe Gemini. Okay, so you see there are a great variety of data you can choose from. Okay, and each of them have different data set, data table, and all those things. So yeah, the volume data is a lot, and yeah, you can actually download them if you are interested. So I will post the link to this if you are interested to play around yourself. Okay, so yes, you can preview the data. They even have images they can extract taken by this particular telescope beside other data. So you can imagine the variety of data. There's a lot of them. Okay. All right. So, and then the next thing is that the machine, we need to process the data. On the right is actually, well, the so-called supercomputer I use in my university. There is actually 145 Dell server put together. Each server have 2 processors. Each processor are 4 cores. So altogether 8 cores. So they have a total of 1,160 cores in this. And look at this guy, 7.3 million cores. So this is actually the fastest computer built by Fujitsu today. Of course, there are other type of supercomputer, which is right now, I think China is in 4th and 5th place. The first 3 is still, the second and third is American, and Japanese is the first one. Okay, so the kind of power that we require to process all this data, and this computer is actually now used to process the COVID-19 genome trying to find a cure for it. Okay. So, okay, so actually, basically, my talk about informations of the universe has over, but I just want to let you know about why astronomy matters. So what happened is, this is a video from a dash cam taken in, I think it's 2013, February 15, 2013. It's still winter, so you can see the sun is actually very low. It's still below the horizons. So an object actually flew across the sky during that time, and it is brighter than the sun. So this is actually an asteroid that hit that area. So the asteroid was entering this place at the 25 times the speed of sound, and it broken every window in that city. Luckily, it never hit the city, but even that, the shock wave itself, with the broken window, a few thousand citizens were injured during this incident. So we are not, we can anticipate something like that may happen sometime in future. Okay, any object that about a kilometer in size hit Earth will wipe out all the living thing on Earth. This has actually happened before. So in 65 million years ago, an asteroid that hit Earth and caused the extinctions of all the dinosaurs. We have to thank this asteroid because of that. Mammal, which is the smaller kind of living thing during that time, have actually survived through the disaster and become the dominant species. And human, as part of the mammal species, have evolved to be the intelligent one. So yeah, why he destroyed all the dinosaurs is that when it hit Earth, the debris itself covered the atmosphere for more than a decade. So first thing that actually died along with it is actually the plants. Okay, the plants need photosynthesis, they need sunlight. So there are two types of dinosaur, the one that meat eater and the other vegetarian dinosaur, the omnivores and the carnivores. Okay, the vegetarian dinosaur will die first because they are very choosy. They only eat plants, and the meat-eating dinosaur eat the dead dinosaur, but they still unable to survive. So whether you're meat eater and vegetarians, no good. You should be all around eater, which is the mammal. They eat everything, so they survive. They eat the carcass and everything. They survive 10 years until the debris have all subsided, and we can see sunlight and plants grow again. And yeah, so don't be too choosy when eating your food. Okay, so but these are not the only way and only thing that actually threaten Earth. So we are doing something bad about ourselves. So we created pollutions. We created extreme weather because of global warming. We have war, and now we have disease. So every of this is everything of can happen to a fragile system, a fragile environment. So eventually, well, it may threaten humanity itself. So astronomy does matter because we will learn how to survive through this by learning more about science. At the same time, we will continue to explore other parts of the universe or even our solar system, and maybe we can create a second home outside of Earth that instead of putting all humanity in one basket, okay, or all the egg in one basket, we can create a second basket, a second home that eventually let humanity continue to live if Earth happen to be somehow destroyed. Okay, so this is a message I want to actually impart on you, and we are doing everything we can to conserve and protect this planet at the same time. So challenge to you, and yes, these are some challenges. Yeah, maybe. Okay, and yeah, that's the end of my presentation.
Well, thank you for the impressive talk. Now we'll move into a short Q&A. So there has been questions on, okay, let's have the first question, which is, how fast do gravitational waves travel?
Nothing can travel faster than the speed of light. So at the moment, the theory is that they will travel at the speed of light or slightly slower. That's the consensus at the moment.
Okay, interesting. Now, the next question is, how can we know that the sun emits mostly green light?
Okay, how do we know the sun emits mostly green light? Interesting question. I actually never thought about it. Okay, very simple. You can actually put filters. So there's this thing called color index that we can do. So basically, color index is something that we use a series of filter. Okay, let me see. I have something here that I can use. Yes. So we can do a photometry of the by putting different filters and see where the strongest light come from. Okay, and compare them. Then we will know that the colors of the sun. So this is actually this is how we measure the color of different stars. In astronomy, we call this the photometry. So example here is that a green filter will let only the green light pass through. Okay, so if you have put different filters here, you'll see where the pit of this filter, and you do okay, we measure actually the magnitude. So how strong is the light that coming in? And we can actually use it to deduce the kind of color. Okay, this is how we know. Yes.
Okay, that's interesting. And now, the next question would be, how to get the wind's displacement constant?
Where you can just Google it. Actually, in any physics books, I think most of them you can find in the constant table.
However, I would just like to add, how did scientists actually derive the value for the constant is actually through another law called the Planck's law. So this is another great law that changed the world. It basically tells us how to use the oven and microwaves. And yeah, and the next question is,
I may add something. So
okay.
the Venn law is actually approximations. So it's actually through observations they come up with the Planck's law. The Venn's law. The Planck's law is more accurate. Actually, is come from it is actually acceptable as part of the manifestations of quantum mechanics. Yeah, the cool word quantum.
Okay. Now, the next question is, what? Just now you did mention about the 26,000 years. What exactly takes 26,000 years, and what is the name of that cycle?
Oh, 26,000 years, the precession itself, the precession cycle, I think you're talking about, right?
Yes.
Yeah, that is called a precession cycle. So if you spin any tops, okay, the top itself will wobble in a circle. That is the thing is called precessions. So what is actually the question? I don't understand the question.
Okay.
These things, right? You're talking about.
Yeah, I think, yeah, this is basically the question.
Ah,
Okay, I think with that, that wraps up today's session because there is another session later on. So, thank you guys for attending this webinar. We hope to see you guys in a future webinar. And also, in we'll also be sending a feedback form to you guys so that you guys can sort of tell us what we could um, improve on for the webinar. So yeah, thank you guys. Yeah.
wait, if I need to post anything, is there any way that I can post? Because I have some links here, maybe in.
I will be emailing them the feedback form, so I think you can also send me the links
Okay,
so
and also
for
the.
the additional material.
Okay, can will do.
Okay, with that, thank you very much for coming and hope you guys safe and healthy and see you guys next time.
Okay, and thanks for staying until the end. I think some parts may be overwhelming. Okay, I'm so sorry. And this is actually one of the most requested talk so far. It's actually, but your version is actually slightly longer than the previous 3 versions. So thank you so much.
Okay, with that, thank you.